In statistics, the standard deviation is a measure that is used to quantify the amount of variation or dispersion of a set of data values. A standard deviation close to zero indicates that the data points tend to be very close to the mean of the set, while a high standard deviation indicates that the data points are spread out over a wider range of values. The standard deviation of a random variable, statistical population, dataset, or probability distribution is the square root of its variance. It is algebraically simpler, though in practice less robust, than the average absolute deviation. A useful property of the standard deviation is that, unlike the variance, it is expressed in the same units as the data. There are also other measures of deviation from the norm, including mean absolute deviation, which provide different mathematical properties from standard deviation. In addition to expressing the variability of a population, the standard deviation is commonly used to measure confidence in statistical conclusions. For example, the margin of error in polling data is determined by calculating the expected standard deviation in the results if the same poll were to be conducted multiple times. This derivation of a standard deviation is often called the standard error of the estimate or standard error of the mean when referring to a mean. It is computed as the standard deviation of all the means that would be computed from that population if an infinite number of samples were drawn and a mean for each sample were computed. It is very important to note that the standard deviation of a population and the standard error of a statistic derived from that population are quite different but related. The reported margin of error of a poll is computed from the standard error of the mean and is typically about twice the standard deviation, the half-width of a 95% confidence interval. In science, researchers commonly report the standard deviation of experimental data, and only effects that fall much farther than 2 standard deviations away from what would have been expected are considered statistically significant. Normal random error or variation in the measurements is in this way distinguished from causal variation. The standard deviation is also important in finance, where the standard deviation on the rate of return on an investment is a measure of the volatility of the investment. When only a sample of data from a population is available, the term standard deviation of the sample or sample standard deviation can refer to either the above-mentioned quantity as applied to those data or to a modified quantity that is a better estimate of the population standard deviation. Basic examples. For a finite set of numbers, the standard deviation is found by taking the square root of the average of the square deviations of the values from their average value. For example, the marks of a class of 8 students are the following 8 values. These 8 data points have the mean of 5. First, calculate the deviations of each data point from the mean, and square the result of each. The variance is the mean of these values, and the population standard deviation is equal to the square root of the variance. This formula is valid only if the 8 values with which we began form the complete population. If the values instead were a random sample drawn from some larger parent population, then we would have divided by 7 instead of 8 in the denominator of the last formula, and then the quantity thus obtained would be called the sample standard deviation. Dividing by n-1 gives a better estimate of the population standard deviation for the larger parent population than dividing by n, which gives a result which is correct for the sample only. This is known as Bessel's correction. As a slightly more complicated real-life example, the average height for adult men in the United States is about 70 inches, with a standard deviation of around 3 inches. This means that most men have a height within 3 inches of the mean, 1 standard deviation, and almost all men have a height within 6 inches of the mean, 2 standard deviations. If the standard deviation were 0, then all men would be exactly 70 inches tall. If the standard deviation were 20 inches, then men would have much more variable heights, with a typical range of about 50 to 90 inches. 3 standard deviations account for 99.7% of the sample population being studied, assuming the distribution is normal. Definition of population values. Let X be a random variable with mean value mu. Here the operator E denotes the average or expected value of X. Then the standard deviation of X is the quantity. In other words, the standard deviation sigma is the square root of the variance of X, i.e., it is the square root of the average value of 2. The standard deviation of a probability distribution is the same as that of a random variable having that distribution. Not all random variables have a standard deviation, since these expected values need not exist. For example, the standard deviation of a random variable that follows a Cauchy distribution is undefined because its expected value mu is undefined. Discrete random variable in the case where X takes random values from a finite data set x1, x2, xn, with each value having the same probability. The standard deviation is or, using summation notation, if, instead of having equal probabilities, the values have different probabilities. Let x1 have probability p1, x2 have probability p2, xn have probability pn. In this case, the standard deviation will be continuous random variable, the standard deviation of a continuous real-valued random variable x with probability density function p is and where the integrals are definite integrals taken for x ranging over the set of possible values of the random variable x. In the case of a parametric family of distributions, the standard deviation can be expressed in terms of the parameters. For example, in the case of the log-normal distribution with parameters mu and sigma 2, the standard deviation is -1 exp 1/2. Estimation. One can find the standard deviation of an entire population in cases where every member of a population is sampled. In cases where that cannot be done, the standard deviation sigma is estimated by examining a random sample taken from the population and computing a statistic of the sample, which is used as an estimate of the population standard deviation. Such a statistic is called an estimator, and the estimator is called a sample standard deviation, and is denoted by S. However, unlike in the case of estimating the population mean, for which the sample mean is a simple estimator with many desirable properties, there is no single estimator for the standard deviation with all these properties. And unbiased estimation of standard deviation is a very technically involved problem. Most often, the standard deviation is estimated using the corrected sample standard deviation, defined below, and this is often referred to as the sample standard deviation, without qualifiers. However, other estimators are better in other respects. The uncorrected estimator yields lower mean squared error, while using n-1.5 almost completely eliminates bias. Uncorrected sample standard deviation. Firstly, the formula for the population standard deviation can be applied to the sample, using the size of the sample as the size of the population. This estimator, denoted by Sn, is known as the uncorrected sample standard deviation, or sometimes the standard deviation of the sample, and is defined as follows. Where are the observed values of the sample items and is the mean value of these observations? While the denominator n stands for the size of the sample, this is the square root of the sample variance, which is the average of the squared deviations about the sample mean. This is a consistent estimator, and is the maximum likelihood estimate when the population is normally distributed. However, this is a biased estimator, as the estimates are generally too low. The bias decreases as sample size grows, dropping off as 1n, and thus is most significant for small or moderate sample sizes, for the bias is below 1%. Thus for very large sample sizes, the uncorrected sample standard deviation is generally acceptable. This estimator also has a uniformly smaller mean-squared error than the corrected sample standard deviation. Corrected sample standard deviation: if the bias sample variance is used to compute an estimate of the population's standard deviation, the result is here taking the square root introduces further downward bias by Jensen's inequality, due to the square root being a concave function. The bias in the variance is easily corrected, but the bias from the square root is more difficult to correct, and depends on the distribution in question. An unbiased estimator for the variance is given by applying Bessel's correction, using n-1 instead of n to yield the unbiased sample variance, denoted S2. This estimator is unbiased if the variance exists and the sample values are drawn independently with replacement. n-1 corresponds to the number of degrees of freedom in the vector of deviations from the mean. Taking square roots reintroduces bias, yielding the corrected sample standard deviation, denoted by S. As explained above, while S2 is an unbiased estimator for the population variance, S is still a biased estimator for the population standard deviation, though markedly less biased than the uncorrected sample standard deviation. The bias is still significant for small samples, and also drops off as 1n as sample size increases. This estimator is commonly used and generally known simply as the sample standard deviation. Unbiased sample standard deviation: for unbiased estimation of standard deviation, there is no formula that works across all distributions, unlike for mean and variance. Instead, S is used as a basis, and is scaled by a correction factor to produce an unbiased estimate. For the normal distribution, an unbiased estimator is given by S, C4, where the correction factor is given in terms of the gamma function, and equals. This arises because the sampling distribution of the sample standard deviation follows a chi distribution, and the correction factor is the mean of the chi distribution. An approximation can be given by replacing n-1 with n-1.5, yielding. The error in this approximation decays quadratically, and it is suited for all but the smallest samples or highest precision. For n equals 3 the bias is equal to 1.3%, and for n equals 9 the bias is already less than 0.1%. For other distributions, the correct formula depends on the distribution, but a rule of thumb is to use the further refinement of the approximation, where gamma-2 denotes the population excess kurtosis. The excess kurtosis may be either known beforehand for certain distributions, or estimated from the data. Confidence interval of a sampled standard deviation: the standard deviation we obtain by sampling a distribution is itself not absolutely accurate, both for mathematical reasons and for practical reasons of measurement. The mathematical effect can be described by the confidence interval, or CI. To show how a larger sample will make the confidence interval more narrow, consider the following examples. For a small population of n equals 2, the 95% CI of the SD is from 0.45 *SD to 31.9 *SD. In other words, the standard deviation of the distribution in 95% of the cases can be larger by a factor of 31 or smaller by a factor of 2. For a larger population of n equals 10, the CI is 0.69 *SD to 1.83 *SD. So even with the sample population of 10, the actual SD can still be almost a factor 2 higher than the sampled SD. For a sample population n equals 100, this is down to 0.88 *SD to 1.16 *SD. To be more certain that the sampled SD is close to the actual SD, we need to sample a large number of points, identities and mathematical properties. The standard deviation is invariant under changes in location, and scales directly with the scale of the random variable. Thus, for a constancy and random variables x and y, The standard deviation of the sum of two random variables can be related to their individual standard deviations and the covariance between them, where and stand for variance and covariance, respectively. The calculation of the sum of square deviations can be related to moments calculated directly from the data. In the following formula, the letter E is interpreted to mean expected value, i.e., mean. The sample standard deviation can be computed as, for a finite population with equal probabilities at all points. We have this means that the standard deviation is equal to the square root of the difference between the average of the squares of the values and the square of the average value. See computational formula for the variance for proof, and for an analogous result for the sample standard deviation.